In this video, we'll talk about radians, kind of where they come from, how to use them, and what they really are. So let's talk first about degrees. So if we think about what a degree is, that's a way of measuring angles. And we have a pretty good idea of what degrees look like. However, if we think about where they really come from, it's a way of measuring angles where I'm looking at 360ths of a circle. And I would question what makes 360 so great. And really, there is no concrete answer. It's just someone picked 360, thought it would be great. There's no reason it's not 400 or 100 or 250 or 7. It could have literally been anything. Now, degrees are useful because everyone in society generally has a pretty good idea of what a 72-degree angle looks like. You know, we've been drilled them since we were really, really young. And the issue is that it's completely arbitrary. Or I guess I shouldn't say that's so much of an issue. It's fine if everyone understands it. But if we think about perhaps another way to think about what a circle would look like. So radians are another way of measuring angles. And I like to think about it as radians are essentially the metric version of degrees. So we're measuring angles based upon arc lengths of unit circles. And we'll talk about what that means here in just a second. So let's talk about a unit circle. Now, a unit circle is a circle with a radius of 1. Could be 1 mile, 1 foot, 1 whatever. It's a unit of 1. So if we think about the circumference of this entire circle, well, circumference is equal to 2 pi times radius. If the radius is 1, the whole way around, in this case of the unit circle, is 2 pi. So if we picture this unit circle, that would be the same as 360 degrees. If I have a 360 degree central angle on this unit circle, the arc length is 2 pi. Now, this right here, this 2 pi, that is a radian measure. And we can do this with every angle in between. So if we think about, let's cut this circle in half. And I just want to know what would the length of that arc be. Well, if the full thing is 2 pi, half of it would be 1 pi. And we also know that to be 180 degrees. Likewise, if I look at just this 90-degree angle here, well, that'd be half of 90, or half of 180, which is 90 degrees. And if I think about the arc length of that little chunk, it'd be half of the green chunk, which would be pi, so pi over 2. And then I could cut that further in half, so if I cut that in half, I would have pi over 4. That's going to be 45 degrees. And then another one that's fairly common, if I take pi over 3, so you're looking up at this guy, or no, this one, and you're dividing it by 3. Okay, if I take 180 degrees divided by 3, that's going to be 60 degrees. And then one last one that's pretty popular. If we look at pi over 6, that'll be 30 degrees. Now, one thing that's worth noting here, radians have no units. So, the purpose of this lesson is to allow you to understand where radian comes from, and what we'll talk about here in just a second is how to convert between radians and degrees. Now, largely the important skill is to convert from radians to degrees, because a lot of computer software will only work with radians. And we'll talk about why that is in a future lesson. But a lot of technology, a lot of computers, a lot of higher order things, a lot of engineers, architects, they will strictly use radians as ways of measuring angles. So it's important to be able to bounce between the two, and that's really the important skill here. So if this is not making a whole lot of sense to you, that's okay. I'm hoping the next part will. So it turns out that there's a pretty simple conversion formula between radians and degrees. As we kind of saw before, it's proportional. If I double the degrees, the radians are doubled. If I cut the radians by 4, same thing with my degrees. So I showed you some popular ones. I wanted to show you kind of where they come from. However, this is the important part right here. So the formula is going to look like this. We know that pi is the same as 180 degrees. And we can say that's going to be equal to some amount of radians, let's call it r, divided by some amount of degrees, d. So the idea is, if I find a degree, or if I know a degree and I want to find a radian, I'll plug in my degrees here, solve for my radians. Or vice versa, if I'm given a radian and I want to know degree, I'll plug in for r, cross multiply, solve for d. And we'll walk through a couple of examples here. So for example, if I want to convert 70 degrees into radians, now this might not be the most popular method, or at least the way of, usually it's pretty rare you go from degrees to radians, normally it's the other way around, but for the sake of completion, I'll show you. So I'm going to write my formula, pi over 180 equals r, because I don't know the radians, over the degrees, which in this case is 70. Okay, I would then cross multiply, because it's proportion. So I'm going to have 180 times r equals 70 times pi. Now I would leave the pi. It allows us to keep this as exact as possible for as long as possible. So then to get r by itself, I would divide by 180. So r is going to equal 70 pi over 180, which we can simplify at least a little bit. Get rid of the zeros here, divide by 10, and we'll get 7 pi over 18. And that is an exact answer. That would be an exact radian. Now, if you're asked to do something with it, that'd be the one you'd want to keep. You can plug it into a calculator using 3.14 for pi and get an estimate to what that would be. However, it's not going to make a whole lot of sense given context. Now let's take a look at probably the more likely of the conversion ways. We'll probably want to look at, okay, if I have some radians, what are they in degrees? Degrees are more easily understandable. That's their benefit. So again, we'll set up our proportion. We'll have pi over 180 equals, in this case I do know the radians, it's going to be pi over 10. That's my radian. And then I'm going to divide that entire thing by d, because I don't know the degrees. Okay, so again, I'm going to cross multiply, and you may notice I have put the pi over 10 in parentheses just to emphasize that it is one entity. So we're going to take 180 times that entity, and we'll multiply pi times d. So I'm going to have pi times d, my degrees, is equal to 180 times pi over 10. Okay, now you may notice if I want to get d by itself, I would divide by pi. Now the cool thing about that, both these pi's are going to cancel, leaving me d is equal to 180 times a tenth. Because remember, when you divide off, technically, you're left with a 1. So a tenth of 180, this would be 18 degrees. Now it's worth noting here, this is a degree. I need to mark that it is degrees. If I give no units, it is generally assumed that it's a radian. So from here on out, if you are giving an answer and you want it to be degrees, make sure you include the symbol. Very, very important. Otherwise, if you're talking about an angle and there are no units, it's generally assumed it's a radian. And there's a huge difference between 18 degrees and 18 radians. You might find yourself asking, why do we bother about radians? What's the point? What makes them beneficial? So there's really two answers to that. One of them I can't really get into this video, and it pertains to graphing software, those kind of things. It's more of the default language of computers. The second benefit of radians is arc length. So if we think about arc length in general, an arc is a part of a circle. And in general, if we're talking about the relationship between an arc and a length, and its radius and the central angle, all that, the formula, if you're talking degrees, and we've talked about this before, the formula would be the arc length is equal to 2 pi r, that would be the whole circle, times theta divided by 360. Essentially, I'm multiplying the whole circumference by whatever fraction of the circle I have. If I have half of a circle, well, I would multiply it by half. If I have a quarter, it'd be a quarter. If I have 72 degrees, I have 72 360ths of the circle. That would be the formula we would use. However, if I think about radians, let's say that's a unit circle right here, pinned around this. It's already got an arc length of its own from this point to this point. And all I have to do is scale it up to match this circle. And we know that all circles are similar, so all I have to do is multiply it by the radius. So the idea behind a radian is that to find arc length, all I have to do is take my radius times whatever my angle is, because this is already an arc length of a unit circle. So all I have to do in this case is just scale it up to match whatever circle I'm talking about, or scale it down if we're talking about a circle with a radius of a half. So, to iterate my point here, we've got an example. I want to know what is the arc length if the central angle is pi over 3 and the radius is 5. So, if we're looking at this, we would have the option to convert our radian, pi over 3, into degrees, and then use the degree formula. And if you prefer to do that, by all means, go ahead and do so. However, if we think about it, sometimes a radian measure is not going to have a very nice degree equivalent. So sometimes it's nicer to actually work with the radians. Now, one benefit here, if we're looking at this, all I have to do, my arc length is going to be my radius, which is 5, times my angle, in this case, because it's a radian, times pi over 3, which means that my length is going to be 5 pi over 3. Now, alternatively, I picked pi over 3 as a good example because I know that to be 60 degrees. We've talked about that previously in this video. If you don't believe me, go ahead, check it in the conversion formula before we proceed. But let's hypothetically, just to show you that it works, let's plug this into our arc length formula. So we're going to do 2 pi r times 60 out of 360, which in this case we know the r to be 5, actually. So what we have here is our length will equal 10 pi times, if I simplify, I know that 360 is can be divided by 66 times. So we will have 1/6 of a circle here, which means that the arc length is going to be 10 pi divided by 6, which reduces to 5 pi over 3. Now, if I'm looking at this, of the two, this red example over here definitely seems to be simpler. So if you're given radians, just go ahead, use the arc length formula. If you're not given radians, then really it's up to you if you want to do the degrees or if you want to convert to radians and then go with it. Now, sometimes they don't have nice equivalents, but that's okay. So, just food for thought. The main part, or the important part of this lesson is that you understand how to convert between the two. And just make sure that if you are giving units on an angle. If it needs to be degrees, you are putting degrees. Otherwise, we assume it's a radian.